All right, so again, good morning, everybody. As you see, first thing there, I want to mention that decided I'm quite confident we will finish chapter 7 tomorrow, in which case our next test will be on Monday. So this coming Monday, July the 20th, and we'll go up through section 7.3. That's what we'll finish up tomorrow. And then Friday, we'll do a little bit of new stuff. We'll talk about the test some more on Friday and take test on Monday. Same process and procedures as the first two tests. I'll send out another email reminding everybody of the procedures, but you've done it a couple times now, so everybody should be pretty familiar with it, but I'll send out an email. Anyway, so today we're going to hopefully see how to apply this formula that we came up with yesterday. And so I want to take just a couple minutes and sort of review and remind you what we did yesterday. We got this formula for shear stress in a beam, VQ over IT. And remind you what everything is. Again, this would be the shear stress located or at the position some distance y prime away from the neutral axis. You're looking at the cross section. B is the internal transverse shear force acting on that particular cross section. Q is the first moment of area, and remind everybody it's the sum of, using the notation he uses in the book, A prime times Y bar prime, where A prime, this is the area above, on that cross section above Y prime, where you're locating or where you're calculating the shear stress. It'd be all the area above that. And you multiply that area times this Y bar prime is the distance from the neutral axis to the centroid of that area, A prime. I is the moment of inertia for the whole cross section about the neutral axis. And T would be the thickness or the width of the cross section there at that distance or location where you're calculating the shear stress. So wherever you're at Y prime, whatever the thickness of the cross section is at that point. And one of the last things we talked about was if you want to find the maximum shear stress acting on that cross section, it's going to occur where this ratio, Q over T, is a maximum. And again, this is one of the last things we talked about, was that Q is always going to be a maximum at the neutral axis. So that would give you the largest numerator. So if your thickness, the denominator, is the smallest at the neutral axis, then that's where this ratio of Q over T is going to be a maximum. So if you're trying to find the maximum shear stress, first thing to do is look at, is the minimum thickness at the neutral axis? And if it is, that's where tau max is going to be. And that's what we're going to find the maximum stress most of the time. One other just reminder, if you go back to the definition of Q, if you're at the top or the bottom surface, there is no area above or below, above the top or below the bottom. So just remind you, tau is going to be 0 at the top and bottom surface. So just the opposite of the bending stress. All right, and so that's what we're going to hopefully do today, is see if we can apply this concept and calculate some shear stresses. Now, I want to do one thing before we look at an actual beam, it's kind of a special case that it doesn't occur, say, a whole lot, but occasionally it will come up, and if it does, there's a nice little quick easy formula you can use on this. And so I want to show you this, and then we'll look at a beam from start to finish. But let's look at this special case first. I can spell special. And so the special case we're looking at, it's a beam with a cross section that has a single solid rectangular cross section. This formula we come up with is only going to be valid for a beam that has a cross section like this. So think like a 2x4. It's a nice rectangular cross section. And this also kind of gives us a good example or applying this formula up there. So if we just take some arbitrary solid rectangular cross section, well, one, I know from symmetry, right, my centroid is going to be right in the center of this thing. All right, so we're looking at a rectangle with some width b and height h. So we got this rectangular area, width b or base, height h. I know my neutral axis is going to be at the centroid. So from symmetry, I know this would be h over 2. And this also would be h over 2. All right, that centroid's right in the middle. Well, in this case, right, T min is at the neutral axis. In fact, the thickness is the same. It doesn't matter where you're at on this cross section. The thickness is B. So it is the minimum. There's not one smaller than that. So I know, like I talked about right up here above that, I know tau max is going to be at the neutral axis. So we need to find what I is for this cross section, and we need to find Q at the neutral axis. And then we'll plug in this formula up here and see what we get. So I, again, for the moment of inertia, that's what the I in this formula up here is. It's the moment of inertia about the neutral axis. Well, it's a rectangle. This was the only one I told you that you were responsible for and you needed to know. And it's 1/12 base times height cubed. Now, Q at the neutral axis, right, we would take, again, if we're looking at the neutral axis, this A prime would be all the area above the neutral axis, right? So this would be A prime, all the area above that. And we need to know what Y bar prime is. We'll call this C prime. This would be Y bar prime, the distance from the neutral axis to the centroid of that area, A prime. So we take A prime times Y bar prime. Now, this area up here, A prime, it's got width B and height H over 2. So it would be B times H over 2. And Y bar prime, the distance from the neutral axis to that centroid would be half of H over 2, which would be H over 4. So let's see if I can do my math right. We got a B, we got H squared, and 2 times 4 is 8. All right. So we got I, we got Q, and we're going to plug in this formula. So I know the tau max, it's going to be V over I, and we're going to plug in Q over T at the neutral axis. That's where our maximum is going to be. So we got V for I, put in 1/12 base times height cubed. Q, we put in B 8 squared over 8. And the thickness is B, right? Thickness thickness at the neutral axis is B. And then we just do some simplifying, and we're going to end up with 12 over 8, which would be reduced to 3/2. We got a V in the numerator. We got a B in the numerator and B squared in the denominator, so we're going to get a B in the denominator. We got an H squared in the numerator and H cubed in the denominator, so we wind up with an H. So we get 3V over 2BH, but BH is just the area. So usually the way you see this is 3/2 B over A. Nice, simple, quick, easy formula. You don't have to know this formula. It's up to you. You're more than welcome. Again, you can use this. But just remember, this is only true for a single solid rectangle. Right, we can't use this for like a combination of rectangles. Like like an I-beam, we break it up into 3 rectangles. We can't. This don't work on that. It has to be just one single rectangle. But if you run into one of those, you're certainly welcome to use this formula. It's quicker and easier, shorter, less work than going through and calculating what I is and calculating what Q is and plugging into this formula. You can just do 3/2 B over A. All right. Just remember and don't try to use this somewhere it's not applicable. All right. Any question about that result? Again, kind of gave us a good example of applying this formula. One last thing before we're going to put some numbers in, work a beam. There's a very good procedure given in the textbook. I would certainly encourage you. Hopefully you're reading all the textbook, but I know some of you don't do that. But this might be something very worth your while to check out, and that is this procedure. And I looked; it's on page 374 in your book. If you want to find it, you can find it quickly there, and go through and read the way he explains step by step of the process. It may be a little bit different than the way that I've explained it, so that might be beneficial to you. So read that, and as always, there's lots of examples in the book. I encourage you to look at the examples in the book as well. All right, so before we go through and see if we can solve this beam, any questions at this point? All right. Again, if somebody needs another moment, speak up. Otherwise, I'm going to get a new sheet of paper. Okay. All right. So let's see if we can solve this one. We're going to find the maximum shear stress in this beam. Oh, I can get my camera not focused. There we go. So find the maximum shear stress in the beam. And let me draw the beam and the loading. have a simply supported beam. Got a pin support at the left end a roller support at the right end B, and 3 applied forces, 100 kilonewtons right in the middle, and then 2 75 kilonewton forces that are applied also down, and it's 0.6 meters between each of these forces. All right, so we got gonna be a 2.4 meter long beam, 3 forces acting down on it, and we're given the cross section. Let me come over here to the side. It's an I-beam. It's nice and symmetric. Hopefully mine will come out somewhat symmetric. As usual, I'm sure it won't be to scale. This is 12 millimeters. This is 12 millimeters. And this is 176 millimeters. And it's 200 millimeters wide. And the thickness here is 8 millimeters. I think I got all my dimensions. We'll find out here shortly. All right, but that's what the cross section of this beam looks like. It's an I-beam, and very common shaped cross section for beams. And I've mentioned this, I think, maybe at least once or maybe more than that. Is the reason an I-beam is shaped like this is for the same amount of material, you get a larger moment of inertia. I very much depends on how far the area is away from the neutral axis. So by taking this steel or whatever this material is and moving it away from the center, you're increasing your moment of inertia. For the same amount of material, which basically means for the same cost, you get a stronger beam. So that's why I-beams are shaped like that. All right, so if we're trying to get the maximum shear stress, right, we need to know what the maximum shear force is. We need to know what the maximum V, what the maximum shear force is. And how we do that is we draw a shear diagram. That's all we're going to need, because we weren't asked to find the maximum bending stress. We'd also need the moment diagram to find maximum moment, but we just need the maximum shear force. So to draw my shear diagram, I need to calculate what these support reactions are. Again, AX is 0. I just left it off of there because we don't have any applied forces in the X direction, so AX is 0. But these we should be able to get just from symmetry, right? I know from symmetry, AY is going to be equal to BY. Again, you look at the loading that's applied. Everything is symmetric. And if it wasn't symmetric, we'd have to calculate these. But AY is going to be equal to BY. It's just going to be half of whatever that total is. So whatever 100 plus 75 divided by 2. Is that 125? So 125 kilonewtons. So anytime you can use symmetry, do so. Less work. All right, so let's draw our shear diagram. So this is the shear. These are kilonewtons. And This is A, this is B. So I know the shear force at the end is going to be equal to that support reaction. So it's going to start out at 125, go straight across, right, till that load changes, and we're going to go down whatever that force is. So if we go down 75, puts me at 50. And then we go straight across. Again, it's constant until the load changes. We go down 100. That would put me at minus 50. And then again, it's constant until we get to this load. And so we go down 75, puts me at minus 125. And again, this checks out. That's the same as BY. So we're pretty confident we got our shear diagram right. So this is where we look at our shear diagram and determine what the maximum shear force is. So here we just want the largest magnitude. Now in this case, the largest positive and the largest negative are the same. But if whichever one of those was larger, that's what we want. We just want the largest magnitude. That's the V we're going to plug in our formula, VQ over IT. Any questions how we found V max? All right. So we need I, right? We need the moment of inertia. So if you come back and look at our cross section here, again, we can make use of symmetry here. I know this is a nice symmetric area. The centroid is going to be right in the middle, halfway. I can draw a horizontal line here. Okay. That's where my neutral axis is. It's got to go through the centroid. And again, due to symmetry, it's going to be halfway, right in the middle. So if this is 176, and this would be half of 176, which is 88. This would be 88 millimeters. Right, so I know the location of the neutral axis just from symmetry. You don't have to calculate where the centroid is. Now I want to calculate the moment of inertia for this area about that neutral axis. So let's see. We can squeeze it in over here right below that. So we could do this a couple of different ways. One, we could break it up into 3 rectangles. I would call maybe this area 1. The centroid of area 1 is going to be located the same place the centroid of the whole thing is. Maybe we'll call this area 2. This centroid is going to be located right in the center of that rectangle. And this area up here we'll call area 3. Its centroid is going to be right in the center of that rectangle. So we could do it this way. Break it up into these 3 rectangles. Get the moment of inertia for each rectangle and add them up. The alternative would be we could look at one big rectangle, right? That's 200 wide by whatever, 176 and 24. It'd be 200. I think it's square. So we could do one big rectangle and then subtract these 2 rectangles, but it's still 3 pieces. So it's really the same amount of work either way. If you do it one way and it's 3 pieces, and you do it, an alternative way and it's 5, then it's definitely to your advantage to be efficient. The fewer pieces you have, the less work you have to do. So either way works. Let's go adding up these 3. Right. So for rectangle 1, we get 1/12 base times height cubed. So 1/12. The base is 8 millimeters. I'm going to go ahead and convert this into meters. We're going to have to get into meters to the 4th eventually anyway. So 8 millimeters is 0.008 meters. So 1/12 base. the height is 176 or 0.176 cubed. And again, its centroid is on the neutral axis, so we don't have to add AD squared. D is 0. All right, so this, again, this would be for rectangle 1. And then we're going to add, all right, come down here for rectangle 2. Again, we've got to do 1/12 base times height cubed. So 1/12. The base is 200 or 0.2 meters. And the height is 12 millimeters, 0.012 cubed. All right, so that's 1/12 base times height cubed for rectangle 2. But here we do have to add AD squared, all right, because this centroid is not located on the neutral axis. It's located that distance away from the neutral axis. Now that distance would be what, 88 plus half of 12, which is 6. So this would be 88 plus half of 12, which is 94 millimeters. So we got to take the area, which is 0.2 times 0.012 times that distance squared, which is, what did I say, 94 or 0.094 meters squared. All right, so this would be the moment of inertia for rectangle 2. Now, 3 is exactly the same, right? If you look at this distance here, D3, it's the same as D2. It's the same size rectangle. It's located the same distance away. So there's no need to write all this out twice. We'll just multiply by 2, and that includes rectangle 2 and 3. And now we just crunch the numbers, add all that up. I got 46.1 times 10 to the negative 6 meters to the 4th. All right, any question about the moment of inertia? All right, well, then we're after the maximum shear stress. So what we discussed at the beginning, first thing to do, look at the neutral axis and see, is that where your minimum thickness is? In this case, the answer is yes, right? Minimum thickness is at the neutral axis. So that's where tau max is going to be. Tau max is at the neutral axis. And that thickness at the neutral axis is 8 millimeters. That is where our maximum shear stress is going to be. So that's what determines what Q is. Q is going to be all the area above or below wherever we're calculating stress. In this case, we're calculating it at the neutral axis. So we need to find what Q is at the neutral axis. And so I'm going to draw a new picture, because if I try to use that same cross section, it's going to get really cluttered. So I'm going to draw a new picture, right? The neutral axis. And I'm just drawing everything above. My pen's not right. So everything above the neutral axis. This is 88 millimeters. This is 12 millimeters. And this is 200 millimeters. And I'll just put it down here. The thickness there is also, no, it's not 12, it's 8 millimeters. right, so this is how we find Q, right? This is what we want, Q at the neutral axis. So we draw all the area above the neutral axis, right? This is going to be my A prime. Now, we're going to have to break this up into two rectangles, right? So we're going to do, again, we'll call this A prime 1, and up here we'll call this A prime 2. So we got two rectangles. We need to locate where the centroid of each of those rectangles are. That's what the y bar prime is. It's going to be this distance. Y bar prime 1 is the distance from the neutral axis to the centroid of area 1. What's up my pen? And this would be y bar prime 2 is the distance from the neutral axis to the centroid of that area. And then we just add those up. So let's see, we can, I think I got all my dimensions on there. So we're gonna take A prime 1 times y bar prime 1, add that to A prime 2 and y bar prime 2. So this area, A1, is 8 millimeters wide by 88 millimeters tall. So I'm gonna put it in meters again. So 0.008 times 0.0, that'd be just 1088. That's the area, A prime 1. And this would be half of 88, right? This would be 88 divided by 2. It's a rectangle. Centroid's right in the middle. So that's 44.044. So I got A prime 1 times y bar prime 1. Now, A prime 2, that's this upper rectangle. It's 200 millimeters wide, 0.2 meters, times 12 millimeters, 0.012. That's the area. And this distance, y bar prime 2, would be 88 plus half of 12. So this would be 88 plus half of 12, which is 94. It's the same as D2 and D3 up here. So it's, I can squeeze this in here, 0.094. And we add those up and we get Q. And I got Q 256.6 times 10 to the negative 6. These are meters cubed. And again, I'm going to pause here for a second. Because as I told you yesterday, there's something about Q that seems to trip students up. So please speak up if you don't understand and see where we got these numbers from and how we calculated Q. Okay. I don't hear anybody, so we got everything we need now, right? We got V, we got Q, we got I, we got T. So now we're good to go. So we can again get tau max. And I know it occurs at the neutral axis, so yeah, it's VQ over IT at the neutral axis. So Vmax 125 kilonewtons. Let's go times 10 to the third, get in newtons. I know if everything's in newtons and meters, my stress will come out in pascals, whatever. Q, 256.6 times 10 to the negative 6. That's Q at the neutral axis. I, 46.1 times 10 to the negative 6. And then T 8 millimeters, that's 0.008 meters. So again, we want it in meters, 0.008. And that will give me the maximum shear stress. That's the shear stress at the neutral axis. And I got, what did I get? 86.95 megapascals. Again, we can just cancel the 10 to the negative 6 there. So you get 86,950,000. But typically, we don't like to write out big numbers like that. That's why we, instead of pascals, we do megapascals. 10 to the 6. All right. So again, we start to finish. We started out with our beam. We used what we learned at the beginning of chapter 6, how to draw a shear diagram to find our maximum shear force. Looking at our cross section, we calculated the moment of inertia. Minimum thickness is at the neutral axis, so that's where the maximum shear stress is going to be. We calculate Q at the neutral axis, plug in our formula, VQ over IT. We got our maximum shear stress. Not necessarily. The question is, will it always be at the point of minimum thickness? If the minimum thickness is at the neutral axis, yes. If the minimum thickness is not at the neutral axis, not necessarily. You would have to actually calculate what the ratio Q over T is at the neutral axis, calculate Q over T where your minimum thickness is, and whichever one of those is larger is going to give you your maximum shear stress. Again, we talked about that at the end of class yesterday. If you turn that I-beam over and make an H-beam out of it, the minimum thickness is not at the neutral axis then, and you would have to actually calculate the numbers to see, but most likely your maximum shear stress probably would be where your minimum thickness is as close to the neutral axis as you can get. But you can't just generally say, that for sure. You would have to actually calculate what Q over T is both places, at the neutral axis and your minimum thickness that's closest to the neutral axis, and see which one's larger. Don't have to do that very often. All right, any other questions? Well, while we got this, before we do anything else, just say, what if we add part B to this problem? Say we want to find the shear stress. We're going to have to get a new sheet of paper to do this at, let's say, point A, where let's come up here and let's say this point A is, let's say 3 millimeters below that top flange. So rather than finding what the maximum shear stress is, say we want to find the shear stress at some other, particular point on this cross section, and we'll just take point A. But the process we're going to do would work for any point. We can choose point A wherever we want to. But let's go. I think I did. Yeah, I did 3 millimeters below that. All right. So the first thing to point out, V doesn't change. That's the maximum shear force on this cross section. I does not change. That's the moment of inertia for that whole cross section. It doesn't matter where you're calculating the shear stress. Right? T could change. If the thickness at A is different than the thickness at the neutral axis, then that would be different. But here, the thickness at A, it happens to be the same. It's 8 millimeters. But just to point out that it could be different, right? If we were looking at some point up here in this top, somewhere up here in this top flange, the thickness would be 200 instead of 8. right? So that could be different. But what is going to change is Q, right? This Q that we calculated here was at the neutral axis. So we used all the area above the neutral axis. If we want to find the shear stress at point A, we need Q at point A. And so that's where we're actually going to have to do some new calculation. Speak up if you need a second. Otherwise, I need to get a new sheet of paper. I'm at the bottom.
Yeah, give me a second.
Okay. All right, so what we're going to do is, instead of using all the area above the neutral axis, we're just going to use all the area above point A. Right? That's how we get Q at point A, is we use all the area above that point. And so Q is going to be smaller. Obviously, we're not smaller than at the neutral axis, because there we used all the area. All right, are we good now?
Yeah, I'm good, thanks.
All right. So I'm going to draw a new picture. I'm going to keep that handy because I may have to go back to that in a second. And again, mine's not going to be to scale. So, but here's point A. And my neutral axis is down here. Put our dimensions on here. This was 200 millimeters. This was 12 millimeters. This was 8 millimeters. And again, obviously mine's not to scale. We chose point A to be 3 millimeters. All right, but how we go about calculating Q is the same, right? But we're not using all the area above the neutral axis now. We're just using this area, right? So when we do Q at A, again, we're going to sum up A prime times Y bar prime. But this now is going to be A prime 1 is just going to be this area. And the centroid is going to be right in the middle. That's Y bar prime 1. Now, this is going to be the same as this is A prime 2. That's going to be the same as it was on when we calculated Q at the neutral axis. That one's not going to change. We don't have to do anything new there. But that would be this. So you get A prime 1. Now it's 8 millimeters Y, 0.008. It's only 3 millimeters tall. And that distance would be, let me go back. I got to look at my previous picture. This was 88 millimeters. So this distance here would be 85 millimeters. So this would be 85 plus half of 3, 1.5, what was that, 86.5 is the distance from the neutral axis to the centroid of that little rectangle. So 0.0865. Now this one's the same, so I'm going back and look at my, this is 0.2 times 0.012. That's the area, and this was what we found was 94 millimeters. And so when we add that up, we're going to get a different value for Q. We're going to get something less than we did when we used all the area above the neutral axis. I got 227.7 times 10 to the negative 6 cubic meters. Right, so if we're trying to get shear stress at A, again, it's dq over it we're using values at A, and Q and T are the ones that can change. T turned out to be the same, but Q is different. V and I don't change. So actually it would be, we'll just do V over I, Q over T, and A would probably be a better way to write it. Anyway, plug in the values for Q and T there. So V was 125 kilonewtons. So for Q here, we got 227.7 times 10 to the negative 6. I was 46.1 times 10 to the negative 6. And the thickness was 8 millimeters. And so we're going to get shear stress less than we did before. We got 77, let's say 0.16 megapascals. It's less than what we got, 86.9 at the neutral axis. Right, so the question here again, if you're asked to find shear stress someplace other than the neutral axis, any point you want to, this is what changes. The thickness could be different than it is at the neutral axis, and Q definitely will be different. So you have, when you plug in this formula, the VQ over IT, that Q has got to be the Q at the location you're calculating the shear stress. In this case, at point A, you just use all the area above point A. So everything from point A up. That's how you calculate the Q. Any question about that? All right, so the very last thing I wanted to do today was just point something out. And this is just FYI. I like to throw in, in the real world, what's done. You see lots of I-beams in the real world. And if you're a structural engineer and you're doing stress analysis, you're going to calculate maximum bending stress, maximum shear stress, and a lot of I-beams. Now, for what we call a wide flange I-beam, so we're talking about an I-beam that has wide flanges. And I've used this term before, but again, I'll point out, make sure everybody's with me terminology-wise. This, when you're looking at an I-beam, that vertical part in the middle is called web, and the top and the bottom horizontal parts there are called flanges. Just some terminology to be familiar with. Well, we just saw how we can calculate what the actual maximum shear stress is. But you go back to, we said before, tau is 0 at the top and the bottom. So those flanges aren't really carrying a whole lot of stress. So the flanges carry a little stress. Most of the shear stress is in the web. Notice you go look at this example we just did. What we found the maximum was 86.95. Right, we went almost all the way to the top of the web, only 3 millimeters from the bottom of that flange. It only went down to 77. Now, as soon as you cross into that flange, look what's going to happen to the thickness. T is going to go from 8 millimeters. When you're up here in the flange, thickness is 200 millimeters. That stress is going to drop dramatically as soon as you cross into that much wider, thicker cross section, the stress goes way down. In fact, and it goes all the way to zero at the very top. So those flanges don't really carry a whole lot of shear stress. So there's a very widely, commonly used in the real world approximation that's used. Approximation, if I can spell that. Is if you want to check the maximum shear stress in an I-beam, you just take whatever the maximum shear force is and divide by the area of the web. Again, this would be the area I'm talking about. It gives you a conservative result. In other words, it's going to give you a shear stress that's going to be close to what the actual maximum is, but it's conservative in that it's going to give you a maximum that's a little bit larger than what it actually is. And so if you've got an existing structure and you want to make sure that the shear stress in this I-beam is, doesn't exceed the allowable, what the maximum can be, rather than going through and calculating Q and I and plugging in VQ over IT, in the real world, engineers just do V over the area of the web, and if it's good for that, it's good, and so you can get this result in less than a minute with a lot less work, right? So just for example, so if you go to that previous example, and we'll calculate this. I'll show you what we get, and then we'll stop. But so for the previous example, Vmax was 125 kilonewtons, but the dimensions was it 176? This was on this previous example. This was 176 millimeters. Yeah, double check, make sure of that. And this was 8 millimeters. So if you find tau max by taking 125 times 10 to the third, divide by the area of the web, 0.176 times 0.008, where I did this somewhere, I got 88.78 megapascals. And again, compare to the actual, tau max was 86.95. So the actual maximum was basically 87 megapascals. And by doing this in probably 30 seconds, I got 88.8, which is a little bit larger than that. But so I know if this is okay, I don't need to go through all the actual calculations and find what the actual maximum is. I can just use this approximation, and I know if this is okay, then certainly the actual, which is going to be a little bit less, is okay. Now, with this being said, on the test Monday, if I ask you to find the maximum shear stress, right, that's doing what we did initially, VQ over IT. This is not the actual maximum. It's an approximation. Right? So on the test, make sure everybody's clear with this. Use tau is VQ over IT. All right, everybody clear? Now, with that being said, if you do have an I-beam, and this only works for an I-beam, by the way, it's a good way to check yourself. If you calculate a maximum shear stress using VQ over IT, again, you can do this in about 30 seconds. If you get something way off, different than you got with VQ over IT, you've made a mistake. Okay, so you can use it to kind of check yourself. And then when you graduate and get out there in the real world and have a job, you can use it all you want to. That's what the rest of the engineers out there are going to be doing. But for now, you need to know how to calculate the actual maximum shear stress, right? So we're out of time. That's the last thing we're going to do in this section. Tomorrow we're going to look at another kind of special situation called built-up beams. That's the last thing we're doing in Chapter 7. We'll do that tomorrow, and that's where your test will go through. All right, so I'm all out. Stop recording, and as always, if you do have questions, stick around. I'll be glad to address that. But let me stop recording.